Integrated Circuits Laboratory. My instructor is Jenny Xie. The topic I want to tell about it is a high-performance CMOS voltage-controlled oscillator for ultra-low voltage operations. Let's start it with my outline. This is my outline. I have divided into the 5 parts. Part of the introduction is combined into the introduction, the circuit, and the design strategy. Today, I'll focus on the circuit and the design strategy. In recent years, some wireless applications have appeared, such as RFID and sensors. Based on the demands, the low cost and low power RFIC have attracted great attention. The voltage-controlled oscillator, which we call the VCO, is a crucial part for the IC. It can generate a stable clock signal and supplying to the backend applications. For example, you can use in the modulation, like the AM wave or the FM wave. Being a crucial part in the RF front ends, the voltage-controlled oscillator is considered as one of the most power-consuming components. So in the study, a power-saving VCO is presented by using the capacitive feedback and forward bias. The circuit can operate it at ultra-low power while maintaining the performance and the phase noise. The circuit is working at 5.6 GHz. Power supply is about 0.6 volt, fabricating in 0.18 micrometer CMOS technology. This is the essential form of the oscillator. The LC oscillator, the inductor, and the capacitor can charge each other to make it oscillate. To maintain the stable oscillation, we'll need the 2 mechanisms. First is a feedback model. The single can continuously loop inside. And the second is the port model. Because feedback model may lose during the session, we'll need the port model to generate the negative resistor to cancel it. As you can see, there are 2 MOSFETs in the middle. The 2 MOSFETs in the middle, the structure we call is the cross-couple pair. It can generate the negative resistance we want. And this is the proposed circuit structure. It combines with the inductor and the feedback capacitor. The figure shows the half small single circuit. The R1 and the R2 is the loss from the inductor. And the real loss can be estimated by the expression. Because the inductor has its own series resistance, we should take this into concern too. And this is our main character today, the feedback capacitor. The single can loop continuously inside. We all know that the capacitor can save the energy, so it works like magic. It can enhance the output swing. With the feature, the single can be amplified better than before. This is the transfer function. The function can determine the amplified ability. The coefficient at 0 to the A4 is listed as below. The function is too complex, but it's not a great deal. All we want is in the next page. If the loop gain is unity, which corresponds to the voltage gain at the oscillation frequency, if we let L1 equal to L2, R1 equal to R2 equal to RP, with proper arrangement, we'll get the relationships between the frequency, the inductor, and the capacitor. Which one influences the frequency the most? C2, right? Yes, C2 is best for tuning. So the control line is connected in there, but it doesn't mean that the C1 is useless. C1 can help C2 for the tuning range. And the ratio, C1 divided by C2, can critically influence on the GN. When the ratio ups, the GN ups. So the design trade-off is to determine the best ratio. The GN versus ratio figure can be seen in this slide. Generally speaking, to achieve our power saving goal, lower ratio is our first considerations. With the bigger GN, the MOSFET may consume more current, but when the GN is smaller to some limit, the MOSFET will encounter a limit. The MOSFET will encounter some limit. And next, a good VCO can be seen by the phase noise. Phase noise is a norm to determine the purity of the output signal. Because in the real world, we can't make the ideal oscillator. What we make is like the ratios. We will see the 1 MHz from the center, this point. we will see this point. And the figure shows the relationships between the phase noise and the capacitor's ratios. When the ratio ups, the phase noise will be better, but it makes a dilemma with before. We discussed that the lower ratio can save the power. So when the ratio drops, the gain drops and will influence on the output power. The output power will be limited. This result may let phase noise getting worse. But in a single model, I said that the capacitor can enhance the output swing, so the output can be compensated. Then, finally, phase noise can be suppressed, so the ratio drops into 0.2. The phase noise can still be suppressed under minus 114 dBc per Hertz. Let's review the most important power saving skill, the forward body bias. If anybody remember what I said in the GN's value, you may be interested in the sentence. When GN is smaller to a point, it may encounter the limit. What is the limit? In microelectronics, we call it the VTH. The full name of VTH is called the threshold voltage. The MOSFET must cross the VTH to start working. Via the technique, we can see that the VTH is not only influenced by itself, but by the VSB. We just need some resistor to bias the body side. Forcing VSB equal to 0, then the VTH will be dropped down. MOSFET can operate it in lower power. So how can we design a power-saving VCO? A flowchart can help you to conclude it. First, select the frequency and the inductor you want. And next, calculate the capacitor you want and select the ratio. Please note, the ratio should be balanced between the phase noise and the power. And then, calculate the final value. If all is clear, you finish the work. Here is a design example. Now, the oscillating frequency is at 5.6 GHz. The power supply is about 0.6 volts. The ratio of the capacitance is between the 0.34 to 0.68. The gain consumes about 8 milliampere per volt. This is the experiment result. With the feedback capacitor, you can see that the tuning range is about 8.1%. The output power is minus 1 dBm. We can see that the capacitor is truly effect on the output wave. And with the FPV technique, the power can be even lower. The voltage is achieved to 0.4 volt. The tuning range is about 0.4%, and the output is about minus 9 dBm. It's about the end. So let's make a conclusion. We presented a power-saving VCO, fabricated in a 0.18 micrometer CMOS technology by using the capacitive feedback and the FPV technique. A significant performance improvement in terms of the upswing, the frequency tuning range, and phase noise is demonstrated. This is the end of my presentation. Thank you for your